asymptotically straight leaky wire.
Okay. I've put my email address up there because the one on the sheet here is wrong. So if you do feel the need to email me, that's the address there, not this one. Well, the setting for our topic is the plane R2 and a piecewise smooth curve gamma, or set of curves extending to infinity, and we consider the Laplace operator on a suitable domain of functions in L2 R2 which satisfy the boundary condition here. N1 and N2 are the normals on the two sides of gamma directed away from gamma, and Q is a given real valued function, generally taken to be positive. And for the domain of H0, a suitable starting point is continuous functions, continuous second derivatives on each side of gamma, and satisfying the boundary conditions. Then H0 is easily seen to be symmetric by Green's theorem applied on the two sides of gamma, and the associated sesquilinear form A0 is as given there, and the integral over R2 there, and the integral along gamma with the Q coefficient in there. S is the arc length along gamma, and if for example Q is a bounded function on gamma, then a trace inequality shows that A0 is semi-bounded below, and its closure A defines the Friedrich extension, or the Friedrich extension H of H0, and H is self-adjoint, and on the basis of 1.1 and 1.2 we can formally write H is H0 minus Q times a delta function. This method of setting up a self-adjoint operator is basically the approach of Exner, and which he developed in several papers, and in particular in the survey article in the proceedings volume of the previous meeting on ARGA. I'd like to discuss some spectral properties of H under these headings. First of all, the discrete spectrum sigma d for a star graph, which I'll come to in a moment, where the Q is a constant, and estimates for the lowest eigenvalue. Secondly, asymptotically straight gamma, and the essential spectrum sigma e. And finally, essential self-adjointness of the original H0 with a possibly unbounded Q. Star graphs. Well, as you will know, a star graph in this context is simply a graph of n infinite, semi-infinite rays emanating from the origin, And in the case where Q is a constant, positive, there are papers by Exner and his co-workers. The references are all up there. Two theorems I'll mention here. First of all, if gamma is an infinite straight line, in other words, just two rays which form a straight line, in that case the essential spectrum is the interval minus a quarter k squared to infinity, and there is no discrete spectrum. And the other theorem complements that for any other star graph that is more than two rays or two rays not forming a straight line, then the essential spectrum is the same, but this time there is a discrete spectrum. There are eigenvalues below minus a quarter k squared. The proof that the essential spectrum is that interval is relatively straightforward, and the main feature of theorem 2.2 here is that there is a discrete spectrum if gamma n is anything other than a straight line. Now the proof of this in the two papers cited there is very technical and relies on a much more general result for any curve gamma with containing a bend or a corner. And what I'd like to do here is just to present a simpler approach to that particular topic by considering the usual variational quotient associated with the operator h, which in this case is there's the integral of grad squared, and there's the integral along gamma divided by the norm squared of f, and the least spectral point lambda naught of h is less than or equal to vf at any f in the suitable domain. We can take f in any suitable domain. So the idea is to try and construct an f naught such that the variational quotient is less than minus a quarter k squared, less than the lower point of the essential spectrum there. And if we can produce such an f naught, then of course we have an estimate for the lowest eigenvalue lambda naught plus of course its existence. Well, there's a result here with Malcolm Brown, Ian Wood, and myself. Reference BEW4 up there. The least eigenvalue for an n-ray star graph, satisfies this inequality. Now the rather complicated, rather lengthy expression now, but for n equals 3, 4, 5, 6, and 10, the multiples of minus k squared which are there are these values here, and the point is that these values are all greater than a quarter. In other words, this lambda naught n, the right hand side, is less than minus a quarter k squared. So it is genuinely the existence and estimate for the lowest eigenvalue. For n equals 2, the multiple turns out to be only 0.134, less than a quarter, so we're not there in the range where the discrete spectrum is supposed to be. So there's no result there for n equals 2 on the basis of theorem 2.3. I'll come back to n equals 2 later. Another result from the same paper is that for the special case of a symmetric graph, when all the angles between the rays are equal, then we have another estimate there, minus quarter k squared and the cosec squared there. Again, giving an estimate when n is greater or equal to 3. Well, I'd just like to indicate the proof of the theorem. In other words, the choice of the test function f naught in the variational quotient. General idea is that with polar coordinates, f naught is a exponential there minus arg theta. G theta has this form. These are the two adjacent rays in the graph. Theta I plus 1, and the idea is that G looks like that convex outward curve. In other words, the minimum values in that sector are, let's say, 1 on the rays. It seems reasonable to take a symmetric choice, symmetric about the midpoint of the rays. The level curves for f naught, and this is going to give the reason for this choice of G, this sort of G. The level curves of f naught have this concave shape because of the minus sign there. And the rationale for this choice, two reasons. First of all, for the symmetric gamma 4, the actual lowest eigenfunction has got level curves which are actually straight lines. The eigenfunction itself is this exponential minus a quarter k mod x plus mod y. So the level curves are mod x plus mod y equals constant. And lambda naught in that case, the lowest eigenvalue is exactly minus a half k squared. So that's a good sort of test sort of example, since the result is actually easily known. Also for the symmetric gamma 6, again in another of Exner's papers, computationally psi naught has again level curves with that concave appearance. So that gave the idea to have this sort of test function. Leaving out obviously the easy details of the calculation, if that f naught is substituted into the vf naught, we get an expression like this with integrals involving the g function. And it seems reasonable to choose the parameter a to minimize the expression here, and this gives us vf naught, and therefore lambda naught n less than or equal to minus k squared n squared over I1 I2. So the idea is to choose G so that it has as I said, minimum value of 1 on the rays. I1 and I2 can be evaluated explicitly, but nice to have an explicit closed form values. And finally, the right hand side is obviously less than minus a quarter k squared. Well, the choice I'd like to feature here quite a simple one. That's just a numerical factor. This is the main part. There's a minus a half there. That's because in the integrals just mentioned, g squared appeared in various denominators. G squared in the denominators. So it's that's the reason for having a minus a half there. T here is theta minus theta I. So that on the ray theta I, for example, t is 0. p beta I there, and that factor makes G unity at the on the ray there. P is a parameter. Perhaps that's the main novelty. I suppose we tried it first of all with p equals 1, then I thought, well, there's no reason why p equals 1 should give the best result, so I put a p in there. And when we do the evaluate I1 and I2 and so on, we get this estimate for lambda naught n. This s here appearing in the denominator involves these betas are the angles between the rays. So the beta I are the angles between the rays. Now, to get a result which is true for all configurations of the graph, the greatest value of S happens to be when it's a symmetric graph. So saying that S is less or equal to its maximum value, we get this inequality for lambda naught n. What's to be the choice for P? Well, it's the choice which obviously minimizes the expression here. A good choice is pi over 2n, and there's a little table of the values comparing the exact p to give the minimum, which minimizes the expression, and there's the value pi over 2n. So you can see there's a very good match. So pi over 2n is a nice one to take, and it gives the formula which was in the statement of the theorem. There's a question here which in fact there are several questions. The first question is one which Exner mentioned in the survey paper. For a given n, is the lowest eigenvalue actually maximized when gamma n is a symmetric graph? And for n equals 4, if you remember, for the symmetric 4 graph, the lowest eigenvalue was minus a half k squared. This is now the value in the general theorem comes quite close to proving that. For n equals 4, it was minus 0.457, so not quite as good as a half, but not far off. For other configurations, rather than this, if the three angles are beta and the other one is 2 pi minus 3 beta in any order, the conjecture is true when beta is less or equal to 0.634 degrees, also when beta is bigger than pi over 2, and it's also true when gamma has angles beta beta, pi minus beta, pi minus beta. So there's some circumstances there where the conjecture is true, at least in the case of the 4-star graph. Coming back now to the case n equals 2, a graph with just two rays. I did have a barrow, but n equals 2. So we've got two rays here. Angle alpha there, maybe obviously acute or obtuse. And the question is, again, is there an f naught such that that variational quotient is less than minus a quarter k squared? In one of the Exner papers, an f naught was produced which worked for alpha between 174.7 degrees and 180 degrees. So quite a very narrow sector there. Sorry. Then in one of our papers with the Malcolm and Ian, we produced an f naught which widened the range to that. So that leads on to question 2 there. Can we get an f naught which gives a more sort of realistic result that in fact there is an eigenvalue below minus a quarter k squared for even small alpha? To be fair to Pavel, in the paper where this narrow range was produced, he also showed that actually the number of eigenvalues increases to infinity as the angle, as the corner gets even sharper. So there are values of alpha where as the graph closes, new eigenvalues are produced. What are the values of alpha where each new eigenvalue appears? And finally, there is a conjecture there that on the behavior of lambda naught alpha when alpha actually is small, so that gamma is nearly a straight line, that it's minus a quarter k squared, just minus a little bit. I don't know what the chances are of producing an f naught to get that at the moment. Perhaps not very high, but it'd be an interesting thing to try and do, I suppose. If this time at the end I'll show the f naughts which did produce these inequalities here. Well, moving away from star graphs now. There is another type of graph for which, again, the essential spectrum is that interval. And again, Exner and his co-workers produced a technical set of conditions which include the idea of asymptotic straightness. And an example of that is where the curvature of gamma is suitably small as s tends to infinity, with some beta bigger than 5/4. And of course that will tell you that these conditions were indeed somewhat technical in nature. Here I'd like to give a different proof of a result akin to that under a simpler idea of asymptotic straightness, which is simply that gamma should lie close to arbitrarily long disjoint line segments as gamma recedes to infinity. These segments can be located generally in the plane. For example, you could have something like that, and indeed the straight line segments need not join up at corners. Gamma could be arbitrary in between any of these straight lines. Just to for convenience, I'll take them to lie along the x-axis, all these segments. So we'll be considering intervals IM of this nature, centered on CM, length 2am, which is going to become large, and they're all lying along the x-axis, disjoint, but in each one, in each x interval, gamma has the equation y equals fx. We need the derivatives, the first three derivatives of f to tend to 0, and we can even allow a non-constant q, but it will be tending to a k as we go to infinity. So that's what I mean by asymptotically straight in this context, that in these disjoint intervals of arbitrarily long length, gamma has a equation y equals fx with fx suitably tending to 0. The result that we again this is the paper BEW2, which is right. As x goes to infinity through the IM, again this coefficient on gamma tends to a constant, and also the derivatives, first two derivatives tend to 0, so it's like a constant. And as I said, the curve is asymptotically straight in my sense. Then the spectrum contains the interval minus a quarter k squared infinity, no longer equal to it, because of course q can be arbitrary elsewhere on gamma, so that's the most that one can expect. There's also a result where the potential, where the coefficient tends to infinity. Again, the derivatives and the equation of the curve suitably small with the derivatives. In this case, the essential spectrum is the whole line. Well, the proof of the theorems follows a familiar result for parallel results for the classical Schrödinger operator. It's a simple idea. It just uses a suitable Weyl-type sequence, and part of the sort of motivation for this is the parallels to in papers E1 and E2. There were parallel results long ago for the ordinary Schrödinger operator with a classical type potential. I don't know how far I want to take these analogies. I know one talks of a delta function potential here, but it isn't really a potential, is it? It's a coefficient along the curve. Anyway, there are these parallel results, and in other questions there will be the matter of how far one can take these analogies. Well, the sequence, the Weyl-type sequence, means that the norm of the operator plus lambda I tends to 0, and as m tends to infinity for a normalized sequence. You could add in weak convergence if you like, but we don't need that. Either for lambda greater or equal to minus k squared in the case of the first theorem, q tending to a constant, or for all lambda in the second theorem. The FM is supported, as in the earlier papers in the classical Schrödinger case. The FM is supported in a large square. Here's the curve gamma close to the x-axis. FM involves a normalization constant, a smoothing factor. The h is this product here is 1 in most of the large square, 0 outside, and comes down from 0 to 1 in a strip round the edge. Then there's an exponential term there, and the choice of u there is to make fm satisfy the boundary condition that was put up to begin with on the curve gamma. Now it turns out the choice of u is a half the coefficient q 1 plus f dash squared to the minus a half. That makes fm satisfy the boundary condition on in this case on the curve gamma there. Then if we work out delta plus lambda I fm, we get a u squared, which comes from here when we differentiate twice with respect to y. and then there's a minus v dash squared which comes from here when we differentiate twice with respect to x. The other terms involve derivatives of f and q, and are put into a em here, also derivatives of h. They all have norms tending to 0 when m goes to infinity. So for the first theorem, where q is tending to a constant, that means u is tending to a half k. U squared gives us a quarter k squared, plus lambda minus v dash squared, so we simply choose v dashed to make that term 0. So there it is, v is that times x. So that is simply the norm of em which tends to 0. That's what's required to produce lambda in the essential spectrum, and that works for all lambda bigger than minus a quarter k squared. And for the other theorem where q is tending to infinity, this time we simply choose v dash to be v dash to be the square root of u squared plus lambda. Again, this makes sense for all lambda because now u is tending to infinity. So whatever lambda is at some ultimately this is a square root of something positive. So again, this term here is 0, and we have the same result as before, but now for all lambda on the line. A couple of simple examples on at least on the second theorem where q is tending to infinity on gamma. The conditions happen to be satisfied when let's say it's a power of x, and the curve itself y equals fx is constant times x to the minus b. Let's say then the conditions are satisfied if a is between 0 and 1 and b is greater than the maximum of positive and bigger than 2a minus 1. And the other example where the conditions on the second theorem are satisfied is where simply q is a constant in each of the ims, and the constants tend to infinity, and am, the length of the im divided by qm also tends to infinity. This leads to one or two other questions. Yeah, well, they're written down there. Again, the analogy with the classical Schrödinger case, this Weil sequence method does produce estimates for the lengths of gaps in the spectrum if the coefficient satisfies suitable, or in that case, the potential satisfies suitable conditions. For example, order lambda to the minus r if the potential is suitably differentiable. References there are E3 and E4. Is there anything similar for the present situation? That's an open question. It may be may not be a sensible question. It's just a question of whether how far the analogy goes. And also in the example here where q is tending to infinity but a is less than 1, it reminds one of the limit point, limit circle classification for the Schrödinger case. In that case, the dividing value of a is 2. Limit circle case, a less than 2, and continuous spectrum. A bigger than 2 takes you into a limit circle case and a discrete spectrum. So the question is a equal to 1? Does that have a similar feature here? What happens if a is bigger than 1? Then the last section here is a bit speculative. Essential self-adjointness and band criteria. the story starts with a paper of Hartmann, H. Back in 1951, who proved that the one-dimensional Sturm-Liouville operator is essentially self-adjoint or limit point case if there's a sequence of intervals, a fixed length in which Q is bounded above, and it can be arbitrary elsewhere. And just what was happening on this sequence of bounded intervals, no matter where they were, and Q could be arbitrary anywhere else, then you've got the essential self-adjointness. This was extended a bit later by myself, where again the intervals are not necessarily bounded in length here, but there's a general condition on Q, again holding in these intervals under certain conditions. Then in a paper with myself and Des Evans and Bryce McLeod, again quite a while ago now, we did the same thing for Schrödinger operators in Rn. Again, conditions on Q in bands around the origin, let's say, infinite sequence of bands, suitable conditions on Q in the bands and Q arbitrary elsewhere, then we got essential self-adjointness. It depends upon some Carter theory and how the domain of the adjoint operator functions there were approximated by well-behaved functions. And so one can ask a similar question here. Are there band criteria on the coefficient Q on bands along gamma n which imply essential self-adjointness of the original H naught? I said this question was speculative because I don't have an answer here, but I have an indicative result, which is that if we consider the operator H an extension of H naught, which is again minus delta, but the domain is W22 on each side of gamma, continuous and satisfies the boundary conditions, but no longer compact support. This operator is can be proved to be symmetric. Again, here are the disjoint pieces. There's a trace in, if we assume there's a trace inequality with the disjoint pieces here, with constants independent of m. As I say, the gamma n, as a simple case, could all be copies of gamma 1. The first of these bands, and say Q less equal to constant on these bands along gamma, then H is symmetric. This of course doesn't get us to essential self-adjointness, but it's a step in that direction, which depends only on conditions on Q in bands along gamma. So the proof uses the methods that we had in that paper there, but minus the Carter theory, and I think it could be quite a big job to extend the Carter theory to a situation where we do have the boundary condition on gamma involved. That can't be dispensed with, because that defines the whole problem. Well, I'll just finish by putting up the list of questions again. So the last question is the one which I've just mentioned, and on that somewhat indecisive note, I shall finish, Malcolm.